Alright, so in this video we're going to continue with the automotive embedded section of our course, and in the last video we stopped at that particular slide here, and we've seen that there was a paradigm shift in 1990. So we have the before 1990 and after the 1990, and there was some kind of evolution when it comes to the automotive ECU. And remember, ECU is short for electronic control units, and these are the computers that can be found in cars and even in aircrafts, airplanes, and the different transportation sectors as well. So before 1990, we had a one function or task per ECU, and this means that it was easier to integrate, etc. However, we can see that there's a problem because it feels like there's a wall in between the different ECUs, and hence the different functionality that could exist in a car. Fair enough. So where's my pointer? I cannot see my pointer anywhere, and here it is. Right, so you can see that one function, one ECU. This is the rule. Alright, so if we need to have some kind of information from a particular sensor here that is connected to the first control unit here, so there's no way that that particular control unit is able to get to that information. Hence, we need to have some kind of redundant sensor that will read the particular information and give it to that particular ECU. So there's no communication whatsoever. However, we could have, if we wanted two ECUs to communicate with each other, all we have to do is connect. Think about a way. Come on, take 3 seconds to make two ECUs back before 1990 to talk to each other. Well, the easiest way is to connect them in a peer-to-peer manner, in the sense of I can connect, the TX RX of two ECUs and make them talk to each other in a way or another. So TX RX in the sense of I can use an input for that one as an output for that one, and an input for that one as an output, and create my own, kind of communication protocol, use one of the standards that exist. Then you can see that it's kind of complex to make ECUs talk to each other, and there's a way easier, there's an easier way to do so. And that happened in 1990, where we can have a bus. So it's an embedded bus, also known as an embedded network, or just a network, or just a bus. And hence the ECUs can share information. This means that instead of multiplying the number of sensors and the things that, wires to connect them in a peer-to-peer manner or something like that, or to duplicate the ECUs in order to have the different functions. So remember, we had one function per ECU, so maybe we can make an ECU host more than one function, or partially or fully, and then communicate the results with the different ECUs. So it's a new paradigm here, and it's a window of opportunity that the automotive actors did benefit from that. So here you can see some kind of bus, and then we can distribute the different functions, well, partially or fully, over the ECUs that are present in our system. Fair enough? In this particular video, I'm caring about the types of buses that might be used inside of a car, and you should think of one particular bus that we mentioned somewhere along our journey together. We'll talk about those. Or remember, so we said that ECUs are thanks to buses and the embedded buses and the communication network that's happening in today's cars. They're sharing info, and from now on, whenever I'm gonna say that I'm sharing a digital information about any kind of object or element or whatever whatsoever, right, I'm gonna call it a signal. So a signal, by definition, is a digital information about anything, about something. It could be temperature, engine temperature, it could be its rotational speed, it could be a sensor about a user being inside the car, it could be an information about the elected president, of course, any relevant information. Fair enough? So a couple of things that you need to know. Let's see. We will have something that is called the number of values to be coded. So if we want to code some kind of information in a digital manner, so we need to be aware of the number of values that the number of values that need to be coded. So the values to be coded. Fair enough? So let's call it nval. And we will see, how we're gonna use this one right away. So in order to know how many bits are needed to code the digital information, so now that we know the number of value of it, all we have to do is apply some mathematical formula, which is a log. base of 2. It doesn't really matter, but I mean, the number of values to be coded is in between 2 to the power of n minus 1, which is the number of needed bits, and 2 to the power of n. So let's imagine that the number of values that I need to code is only 3. Fair enough. So the number of bits, of needed bits, will be 2. Fair enough, because with 2 I can go ahead and represent up to 4 different values, and I only need 3, so we're good here. So 3 is in between 2 to the power of 2, so 2 bits, so 4 decimal, and it's more or equal than 2 to the power of 2 minus 1, which is 2, so we're good. So 3 is in between 2 and 4, so we're good. Right, so how many bits are needed to code the number of values? Right, so especially in the automotive industry, an extremely interesting thing is the type of the signal that I need to represent or to code. And this is important. How come? Because it's, I mean, the two available types are either signed or unsigned ends. So anything could be represented with the signed or unsigned ends. So what's the difference? Well, why would that be important? Take a second to think about it. So let's start with the non-signed ends. A non-signed integer is, will be representing values with a minimum value of 0 to whatever maximum value we can get with the n bits. Fair enough? What would change with the signed ends? Well, instead of going from 0 to n, right, we will go between two values. Let's call them for now a and b, and the 0 will be in between here. So yeah, with signed we can hit a negative value. So maybe for some reason we need for our signal to represent it. It could be temperature, it could be anything at all. Unlike the rotational speed, for instance, which normally should be unsigned, or maybe signed as well if we are representing a reversed rotational speed. So it really depends on the things that you want to implement. Alright, so alright, so this is an important thing. Let me try and wipe it. Yep. Alright, so there's something that we call the brood value, and we will see what is that. So with the type and with a bunch of bits, we're going to create a brood value. Fair enough? And then to represent the real value, we're going to see what kind of formula we're going to apply to it. Right, so let's see. There's something that we're going to call an offset, and something that we're going to call a resolution, also known as factor. Factor, that's a weird word. Alright, and there it goes. So my brood value, where's my laser pointer? So my brood value that I got from the type and the number of bits, right? So it's a function of the type and the number of bits. I'm gonna multiply it by the resolution, of course, because if I have a resolution of 1 or a smaller resolution or a bigger resolution, the number of steps would change. And we've seen that in the IRF pin example, for instance. We've seen that, the impact of the resolution on the step size. And then we can apply, we have the possibility to apply an offset for a reason. Fair enough? So the offset could be 0, so only the real physical value of the information that we need to represent is only dictated by the brood value and the resolution of it, and that's it. Or we can add to it some kind of offset, right? It's for some mathematical formula that will lead us there. So let's see an example that would be way easier for you to understand, I hope. Alright, so let's see. In this slide we're finding out the name of the signal we're gonna talk about, and you can see the name here and you can see it here, and then you can deduce that it's ENG power. It stands for engine power. Fair enough. And we're using 16 bits to represent that particular signal. Alright, so keep that in mind. Right, and we're seeing that the value of the signal is unsigned, so the values would start from 0 all the way up to a number that is dictated by the number of bits that we're using here. So with 16 bits we can represent how many values in total? So it's 2 to the power of 16, so normally it should be 65,536. Fair enough? And because if it's unsigned, so basically we would be able to go from 0, which would be the minimum value, all the way up to 2 to the power of 16 minus 1, which would be 65,535. Fair enough? So this is the brute signal, and this is the brute signal. So we're good for that. Alright, so you can notice here a couple of things that I didn't talk about earlier, but I mean they're so intuitive. So you have the byte order. That's another name for the endianness of the bytes, right? So it's little endian or big endian. However, in the industry usually we refer to those as Intel and Motorola, right? So Motorola is rather big endian and Intel is little endian. Fair enough? Please double check that. And then units, the unit is intuitive as well, so we are talking about engine power, so it's in kilowatts. Fair enough? Alright, so we have root values going from 0 to 2 to the power of 16 minus 1, so 65,535. However, if we want the physical value, the real physical value, well, we need to apply to it, as we've seen in the formula from the previous slide, we need to apply to it the resolution, also known as factor, and the offset. So here it's easy, we have no offset, all we have to do is apply the resolution. So all we have to do is multiply whatever value we have with 0.01. Hence, the minimum, which is calculated automatically by the way, so the minimum would go from 0 because it's unsigned, so we do not hit the negative values, to a maximum of 2 to the power of 16 times 0.01. Fair enough? So this would be the highest value. So it's 655.35 kilowatts. And this is the maximum engine power that we can have, which makes sense. We good? So, yep, we're good. So this is the minimum of the physical value and the maximum of the physical value that we got by applying the factor and offset that does not exist here to the brute value that we got from the number of bits and the type of the signal that we want to represent. Alright, and by the way, the signal is part of one of the messages that's sent by someone and received by other ECUs. Right, so let's see another example. So here, take a second to try to draw conclusions about that particular signal. So yeah, let's start by the name. So it's called status. So most probably it's status about something, and most probably it's the status about the ECU, and we can deduce from here. But let us not put the cart before the horses, or the horse. Il faut pas mettre la charrue avant les bœufs. Voilà. And how many bits are we using to represent that particular signal here? So we're using 2 bits, so we can have up to 4 values, which makes sense. And we're using Intel, it's an unsigned, and we have no unit, which makes sense because it's a status. However, here there's something, so we have no resolution and no offset, so the resolution is 1, so we're good. We don't have smaller or bigger steps. However, here it feels like we're not using the maximum and minimum value, and it makes sense because we're not representing a physical value, we're representing a state of something. Hence, we're going to use the value table here, fair enough, which is represented by that. This means that whenever we have the value 0, right, so we have 2 bits, so we can have up to 4 values, so we have 0, 1, 2, 3. So whenever we have the value 0, this means that my ECU is awake, so wake up. When we have 1, it means that it's running. When we have 2, it means that we're going to sleep, and when we have 3, it means that we have an error. Fair enough? So instead of representing a physical value here, we're representing 4 different states, and we're using 2 bits to represent those states. So we can see we can represent, virtually anything, and share the information on the bus. And by the way, this is a screenshot from the software tool developed by Vector, Germany, and it's called Canoe, and this is the emulator of the CAN bus that we'll talk about later in that video and in the upcoming one as well. Alright, so speaking of the devil, let's check the different buses that exist in the cars today. So let's forget about the logos that are here. Let me try and understand the schematic here. So apparently the y axis here represents the speed and the speed. There's another word for speed that I taught you in class this year. In bits per seconds, alright? And then we can see the evolution throughout time. So we have this timeline here. Alright, so I'm interested in that one, and that one. So len here. So we can see it's rather a low speed bit rate, 20k, which is not bad, but I mean it's low compared to the others. Alright, and we started using it here around 1998-ish, 70-ish, right? And then we have the flex ray, right? Early 2000, this is correct, I remember that. Alright, and this is used in high-end cars. So if you own a BMW or an Audi or a Mercedes, there are high chances that you're gonna find a flex ray bus in your car. Right, so 5 megabits per second, which is good. And the highest speed bus among the 3 here is the most, and it's apparently used for infotainment, and we talked about that in a previous lecture. So infotainment is the concatenation of 2 words, information and entertainment, right? So basically this is anything related to multimedia, the radio, maybe videos, maybe sharing messages, real-time messages, video messages and stuff like that, for entertainment and information delivery related, right? And it can reach up to 25 megabits per second, which is extremely high, right? And you can see that also this one is used in high-end cars as well. Okay, and something that we have mentioned but didn't really talk about yet, right? You can see that there's a CAN bus here, and we can see the different speeds and the timeline. Right, so let's switch to that particular schematic here, so we can see the len with the speeds, the bitrate again. However, this time on the x, the axis here, the x-axis is the cost of the node. So what's a node? A node is another name of an ECU, right? So especially when an ECU is connected to a bus, we call it a node, right? So it's a peripheral, a computational peripheral, or an ECU, or an embedded computer, and it's a node that can be found on a bus. And here you can notice that the len is usually the cost of the peripherals here, because they are low-cost microcontrollers and or sensors, actuators, and stuff. You connect bunch of sensors and actuators usually. And so yeah, so it's rather low cost here. And then with the CAN, it's higher speed and a little bit higher cost. And then the most expensive ones are usually the flex ray, and usually the most as well. Fair enough? So let's have a couple of words about those 3 buses here, and then we're gonna go and tackle in more details the CAN bus, which is extremely ubiquitous and can be found in most cars today, if not all. Alright, so let's see. Len bus. aka local interconnected network. This is what enables the connection of sensors and actuators in a small subnet, right? So this could be a small network or small bus used to connect and integrate the different sensors and actuators in an inexpensive manner. And then this particular subnet can connect to the main bus of the car or another bus in the car using a gateway, for instance, right? So systematically from now on, whenever you think sensors and actuators, usually you connect them with a low speed, low cost LIN bus. Right, next we have the flex tray. So the flex tray is something that is expensive, I can tell you that. But not only it's expensive for a reason, because it was designed to serve security and safety critical applications, right? And it has an intrinsic deterministic time responses. So it improves determinism, and it's extremely important in the automotive industry because, again, it's a real-time context, right? And it's designed to be redundant, hence the extra cost. Last thing I want to talk about is the MOST, so the media-oriented system transport, and this was being introduced and dedicated especially for multimedia information, so infotainment ECUs, right? And it has, I mean, the good thing about it, because they're multimedia require a high speed bandwidth, so a high bandwidth and high throughput and high bitrate, fair enough. So the MOST is designed for that particular reason. This doesn't mean that there are those are the exclusive buses and communication channels, no, communication media that are used exclusively in cars. There was an attempt to use Ethernet. So Ethernet, from your local area network, from the internet, from the network course that you might have had here at GUC. I really hope so. The automotive version of the Ethernet, right? So Ethernet wasn't meant to be used in the automotive industry because it's a mature technology of over 30 years, I believe, in the networking markets. So and LANs and stuff like that. It was developed in the 1970s, but it's an extremely interesting protocol. However, in the automotive industry, it's been used primarily for diagnostics, in-vehicle infotainment, and maybe sometimes connect sensors as well. Usually, people from the automotive industry, they try to use Ethernet for anything that is data heavy. Systems that require a great bandwidth to transmit data, and it is a serious competitor to the other buses. So what would be the benefits? It's extremely important for those of you who are interested in the autonomous paradigm, so autonomous vehicles. So yeah, definitely you will be connecting a lot of stuff to function effectively. You will be having cameras, lidars, and other sensors for traffic signs recognition, for instance, and maybe for some connectivity like the V2X paradigm. So yeah, with the speed of around 100 megabits per second, if I'm not mistaken, in its current form. I think Ethernet will also reach faster speeds later, I mean soon. And it's a huge rival for the most, that's for sure, when it comes to multimedia, and it could be used, for the different things because it's rather cheap and we're used to that. However, it has so many challenges that we could talk about those maybe later sometimes. I mean, this is one of the buses or the protocols that are publicly used that could be used in the automotive industry as well. And we can imagine others such as Bluetooth or something like that to go wireless maybe for some particular applications, especially soft real-time or non-real-time, remember. Alright, so let's talk a little bit of, I don't know, the CAN now, the most, predominant one. ISO 118980, 8, not 80. So what can I say about the CAN bus? As an overview, I would say that we've seen that it is one of the buses, and it's the predominant bus used in cars, and it's definitely used to connect ECUs, and hence connected ECUs, they're also known as nodes, as we said before. Fair enough. And we've already said that the number of ECUs is extremely huge in cars today, so we can have even more than 70, 80, maybe 100 ECUs in average cars. Maybe more in high-end cars as well. So what's so special about the CAN bus? It's simple and it's low cost, right? So this is the biggest advantage of it all. And it's rather efficient, hence it's widespread, it's used everywhere. It's rather robust, right? And we're gonna see that its principles is really based on something that we call broadcasting. Fair enough. So any ECU that might be connected to a sensor, for instance, can prepare the information, the digital information, that it got from that sensor. And another name for digital information is the signal, right? So can share that signal in a CAN message with every ECU that is present on the CAN bus, and the ECUs who are interested in that particular signal will get it, and the others will just ignore it. And we're gonna talk about those in details. Let's have a quick history about the CAN. So the CAN bus, before the CAN bus happened, so it's, if we wanted to make ECUs or nodes talk to each other, we relied on peer-to-peer or point-to-point wiring. 1986, yep, old times. So that was developed by the German Bosch. So they created it and they used it with their OEMs, with their the different companies that they work with. It's an in-house protocol, so it's made to be used with and for the Bosch related equipment, right? In 1991 now, there's a newer version of the CAN bus that has been open source, published publicly for anyone to see and use. However, it wasn't a standard yet. The standard happened in 1993, so this is where it has been adopted as a ISO standard, right? So 11898, and then in 10 years later, it became a series of standards, meaning that we can have a new version of it, we can add some stuff on it, maybe add some particular advantages. There's usually advantages and no drawbacks, but new features, and then we can have it as, you know, a standard 11.898.1.2.3, etc. 2012, Bosch released the CAN FD, and FD stands for flexible data rate. And here you can feel that apparently if the flexible data rate, the word flexible, this means that maybe we can reach higher bit rates with the CAN FD. What else can I tell you about CAN FD? I can tell you that it became a standard as well in 2015. Alright, and I think that's pretty much, you know, the things that I want to tell you about the CAN Bosch. Yeah, and ever since, you know, since then it's reaching higher bit rates than the original ones, of course, because there's always a demand for higher bit rates. Right, so let's see so quickly the schematic here. So CAN bus, we can find the word here. So CAN bus line, so physically it's made out of two lines. Hold on, so two lines, is it synchronous or asynchronous? I mean, two lines for something that you know, for ECUs sharing information, so most definitely this is a serial bus for sure. However, the idea is to find out if it's synchronous or asynchronous. So apparently, because we have CAN high and CAN low, someone might think that it's a synchronous one. However, nope, none of the lines is dedicated for clock impulses, so it's not a synchronous protocol. It's a it's a asynchronous one. However, the physical implementation, there's a reason for that, and we're gonna find out about that later in a later video. Right, so here, as I told you before, anything that is connected to the CAN bus is also known as, from now on, a node. So here you can see that we have n nodes, and this could be anything. So that anything should have a CAN controller in order to be able to understand and to use the bus, and a CAN transceiver, and this is to be able to get the bits, right? So physically get the bits, the physical layer, and then some upper layer in order to know how to understand the different fields in a message, for instance. Fair enough? Could be DSP, so digital signal processor, or a microcontroller, or anything. Alright, so let's go. Alright, so yeah, asynchronous serial, we got that. And I said earlier that is based on broadcasting, so we're gonna broadcast some messages, and those who are interested in it will use it, and those who are not interested in it will just discard it. Plus, we're seeing another notion here that we've seen earlier with the I2C bus, for instance. It's a multi-master. So systematically, when we have multi-master, what are the two things that we need to care? I mean, what is the thing that we need to care about? So yeah, definitely, if it were a synchronous system, this means that we needed to synchronize the clocks. But thankfully, this is an asynchronous one, so we don't care about any, you know, synchronization between the clocks. So there are no clocks to synchronize, so we're good. However, multi-master means that maybe two or more nodes can try and control the bus. So this means that we need to, what is the word here? We need to arbitrate. All right, so we need to arbitrate between the different masters in order to, you know, make one of them win and one of them and the others lose. So we can have, you know, some kind of clear and clean information circulating on the bus. Alright, so I'm gonna end up this presentation, this video, with the CAN frame here. So this is the CAN message here, and I want you to see the different fields, just to see them for now, and then we're gonna try and get anything that we might understand without reading any definitions. So SOF, EOF, maybe IFS, maybe. Here's something interesting, and here's something interesting. Maybe something interesting here as well, and definitely here. Alright, so first things first, SOF, that could be start of frame, and if we have a start of frame, we should have end of frame, that's for sure. IFS, that's interesting, we'll talk about that later. Maybe it's something to make sure that the messages are not jammed in a way or another. I mean, they're not touching each other, if I dare to say. There's enough space, so that would be inner frame space, maybe we'll find out later. Important thing is the identifier of the message, right? So maybe this is what we're gonna use in order to arbitrate between the different messages circulating on the bus. And yeah, so here we can see that we can go from 0 to 8 bytes of data, so anything in between 0 and 8 bytes. Maybe some checksum, something to validate the data, to check the validity of the data, maybe some acknowledgement to see if someone is getting or anyone is getting the message. We're gonna see those later. So yeah, so we need to notice that we have a beginning of a frame, an end of a frame, and then the size of the actual data that we are interested in. Alright.